Good day to everyone. I'm Christian Poti DALIZON, and I am here to discuss the topic that is assigned to me, the language of relations and functions. Just for a brief introduction, a relation is a rule that relates values from a set of values called the domain to a second set of values called the range. Um, a relation is also shows the relationship between input and output, and lastly a relation is also a set of ordered pair x and y. Note, all functions are relations but not all relations are functions. So let's head to the given problem that is assigned to me. uh where is it? So here's the given problem. It states that let set c equals to set d equals -3, -2, -1, 1, 2, 3, and define a relation S from set C to set D as follows. For all x and y is an element of the product set C and set D. So it states here that x and y is an element of relation S, which means that 1 over x minus 1 over y is an integer. Uh, For the problem A, is 2 related to 2, is -1 related to -1, is 2 and 2 an element of relation S, is 2 and -2 an element of relation S, and for problem B, write S as a set of ordered pairs. For problem C, write the domain and codomain of S, and for problem D, draw an arrow diagram for S. So let's head to the problem A. Here are the solutions and the explanations as I proceed. Is 2 related to 2? The answer is yes, because by using the formula given, which states that x and y is an element of relation S, means that 1 over x minus 1 over y is an integer. This means that if we use this formula 1 over x minus 1 over y, if the result is an integer, then it is a element of relation S. So for the problem A, 1 is 2 related to 2. By using the formula 1 over 2 minus 1 over 2, the answer is 0, and 0 is an integer. So therefore, it is an element of relation S. So for problem 1 is 2 related to 2, the answer is yes. So for problem A2 is -1 related to -1, the answer is also yes. And just by using the formula 1 over -1 minus 1 over -1, the answer is also 0, which is an integer, and therefore it is also an element of relation S. And for problem A3 is 2 and 2 an element of relation S? The answer is yes, because since 2 is related to 2, therefore 2 and 2 must be an element of relation S. And heading to problem A4, is 2 and -2 an element of relation S? The answer is also yes. By using again the formula 1 over 2 minus 1 over -2 equals to 1, and 1 is an integer, so therefore it is an element of relation S. And for problem B, write S as a set of ordered pairs. So in our given, it's it just states the given -3, -2, -1, and 1, 2, 3. I've been confused earlier because it is just gives one set of numbers, but since it says let set C equals to set D, it must mean that set C and set D has just the same given values, or the given numbers. So I just assume that C and D have the same numbers. So -3, -2, -1, and 1, 2, 3 are for set C, and for the same as set D, -3, -2, -1, 1, 2, 3. And in order to find the set of ordered pairs, we must first find the product of set C and set D. So to do that, we just have to multiply negative 3 set C to set D, which goes by negative 3 times negative 3, and we just pair them up. So negative, and next is negative 3 and then negative 2, and then we just pair them up, and then negative 3 and then negative 1, and then we just pair them up, and so on until we completed the cycle. And after we completed the product of set C and set D, we must look for the every element set in the product of set C and set D where 1 over x minus 1 over y is an integer or not. The x here is the range and the y is the domain. So if the result is an integer, then it is an element of S, of relation S. Then, and here's an examples, because if we do this, if I have done this every element above, it would take ages. So I just gave an example. The first example is the first element in the product of set C and set D is negative 3 and negative 3. So we just substitute the negative 3 and negative 3 to the formula, just like we did in the problem A. So 1 over negative 3 minus 1 over negative 3, which is 0. So it is an integer, which means that it is an element of relation S. So if we got an integer number, we are including it in the set of ordered pairs. So if not, then not. Then we will not include it in the set of ordered pairs. So other example is 1 over negative 3 minus 1 over negative 2. The answer is 0.17, which is not an integer. So negative 3 and negative 2, the pair of number, the pair of number negative 3 and negative 2 is not an integer. So we will not include it in the set of ordered pairs. So just by doing what is included in the example, we are going to find the set of ordered pairs. And what I've found is the in my conclusion, the set of ordered pairs are gonna be negative 3 and negative 3, since they ha- and negative since they have an integer, a result of an integer. Then negative 2 and negative 2, negative 1 and negative 1, 1 and 1, 2 and 2, 3 and 3, negative 1 and 1, 1 and negative 1, negative 2 and 2, and 2 and negative 2. So that is the set of ordered pairs. Again, we found the set of ordered pairs ju- just by using the formula 1 over x minus 1 over y, and if the result is an integer, then we are going to include it in the set of ordered pairs. So let's head to problem C. Write the domain and codomain of S, of relation S. So the domain of S is negative 3, negative 2, negative 1, 1, 2, 3. And since we only have given one given problem set of numbers, and I assume that set C, and since it says in the given that set C is equals to set D, then they must have the same given numbers. So the domain and the codomain are just the same. And for the arrow diagram for relation S, here it is. So the arrow diagram and the set of ordered pairs are connected to each other. So in the ordered pairs, negative 3 and negative 3, we just connect negative 3 and negative 3. Negative 2 and negative 2, we just connect negative 2 and negative 2. Negative 1 and negative 1, we just connect them, and so on. We just connect the numbers here in the ordered pairs and represent them as an arrow diagram for relation S. So that is all. Thank you for listening. That is all.